In the absolute darkness between stars, something moves. It's larger than Jupiter, colder than anything you can imagine, and it's been falling through the void for billions of years. No sun warms its surface, no light reaches its frozen storms. It exists in perpetual night, a world that should be impossible, hurtling through the cosmic dark at hundreds of thousands of kilometers per hour. Scientists call them rogue planets, orphaned worlds ejected from their birth systems, condemned to wander the galaxy forever. And here's what keeps astronomers awake at night. We've discovered thousands of them, but we can't see most of them. They're invisible, dark, silent. And the evidence suggests one might be heading toward us right now. What happens when a rogue planet enters our solar system? The answer isn't just troubling, it's catastrophic. Because gravity doesn't negotiate, physics doesn't compromise, and a world moving at interstellar speeds doesn't stop. Today, we journey through evidence that challenges everything we thought we knew about planetary stability, orbital mechanics, and the fragility of our cosmic home. Prepare yourselves. We begin. In 2011, astronomers using the MOA-2 telescope in New Zealand detected something extraordinary. A planet, alone, drifting through space with no star to orbit. They designated it MOA-2011-BLG-262, and it changed everything we understood about planetary systems. This wasn't a planet waiting to be captured by a star. It wasn't in transition between systems. It was a permanent wanderer, a Jupiter-mass world moving through interstellar space at approximately 30 kilometers per second, completely independent, utterly alone. Dr. Takahiro Sumi, the lead researcher, made a startling calculation. For every star in the Milky Way, there could be 2 Jupiter-mass rogue planets wandering in darkness. Think about that. 400 billion stars in our galaxy, 800 billion rogue planets, maybe more. The universe, it turned out, is filled with invisible orphans. But how does a planet, a world that formed in the stable disk around a young star, end up cast into eternal darkness? The answer lies in the chaotic early days of planetary system formation. Picture our solar system 4 billion years ago. Planets forming, orbits unstable, worlds still migrating through clouds of gas and debris. Jupiter and Saturn locked in gravitational resonance, their massive bulk warping space around them. In this cosmic ballet, one wrong gravitational encounter can change everything. When planets interact, when Jupiter swings past Saturn, when a Neptune-sized world crosses paths with a forming super-Earth, gravity acts like a slingshot. One planet gains energy, the other loses it. The winner stays in the system, the loser gets ejected, expelled into interstellar space at speeds exceeding the escape velocity of its birth system. It happens fast. In simulations run by astrophysicist Hagai Peretz at the Technion Institute, planetary ejections occur within just a few million years of system formation. One gravitational encounter, one close pass, and a world is condemned to eternal night. Our own solar system likely ejected several planets during its turbulent youth, worlds that should have orbited our sun, now wandering the galaxy, frozen and forgotten. Here's where the story gets disturbing. Rogue planets are almost impossible to detect. They emit no light. They reflect nothing. In the absolute darkness of interstellar space, they're essentially invisible, black spheres moving through blackness. The only way we found them is through gravitational microlensing, a technique that detects how a rogue planet's gravity bends the light from stars behind it. For a few hours or days, the planet acts as a lens, briefly magnifying a distant star before vanishing back into darkness. We found maybe 24 confirmed rogue planets this way, but the mathematics suggests something terrifying. There could be trillions of them in our galaxy alone. Dr. Louis Strigari from Stanford University calculated the numbers. His research, published in the monthly notices of the Royal Astronomical Society, suggests that rogue planets outnumber stars by a factor of 100,000 to 1. 100,000 rogue planets for every star. Most are small, Earth-sized or smaller, but many are massive, super Jupiters, brown dwarf planets. Some might be even larger, massive enough to generate their own heat through gravitational compression, sustaining underground oceans beneath kilometers of ice. And they're everywhere, moving through the galaxy like invisible bullets, silent, dark, undetectable until they're already here. In 2020, a team at Osaka University ran simulations to calculate the probability of a rogue planet entering our solar system. The results were sobering. Within the next million years, the probability approaches 100%. Within the next 10 million years, multiple rogue planets will pass through our neighborhood. And within the lifetime of our sun, about 5 billion years remaining, dozens of rogue worlds will penetrate the Oort cloud, potentially disrupting the delicate orbital mechanics that keep our planet stable. But here's the truly disturbing calculation. The nearest rogue planet to Earth could be just 10 to 20 light-years away. At typical interstellar velocities, that's a few 100,000 years of travel time. If one is heading toward us now, aimed directly at our solar system by pure chance, we wouldn't know until it was already here, because we can't see them coming. But this represents just one piece of a much larger puzzle. The evidence suggests that rogue planet encounters aren't just theoretical possibilities. They may have already happened. Beyond Neptune, in the frozen outer reaches of our solar system, lies the scattered disk, a region of icy objects with wildly eccentric orbits. These objects shouldn't exist in their current configuration. Their orbits are too elongated, too tilted, too chaotic to have formed naturally in a stable system. Sedna, discovered in 2003, orbits the Sun at distances ranging from 76 AU to 937 AU. That's 937 times farther from the Sun than Earth. Its orbit is so extreme that it takes 11,400 years to complete a single revolution. What could create such an orbit? Dr. Michael Brown from Caltech, who discovered Sedna, stated plainly, "Sedna shouldn't be where it is. There's no way to put Sedna where it is. It never comes close enough to be affected by the Sun, but it never goes far enough away to be affected by other stars, unless something massive passed through." Computer simulations by Alessandro Morbidelli show that a close encounter with a rogue planet, a Jupiter mass interloper, passing within a few hundred AU of the Sun, would scatter outer solar system objects into exactly these kinds of bizarre orbits. The scattered disk isn't just unusual, it's a signature, a gravitational fingerprint left by something that shouldn't be here. Here's something most people don't know. Our entire solar system is tilted. The Sun's equator is inclined by 6 degrees relative to the plane in which the planets orbit. That might not sound like much, but it's enormous on cosmic scales. When our solar system formed from a rotating disk of gas and dust, everything should have aligned. The Sun's equator, the planetary orbits, all in the same plane, all perfectly synchronized. But something knocked us off kilter. Research published in 2022 by scientists at the University of Geneva suggests that early in our solar system's history, within the first 10 million years, a massive object passed through, gravitationally torquing the entire system. Not another star. Stars are too bright, too obvious. We'd see evidence of their passage in other ways. But a rogue planet, though? Dark, massive, moving fast? That would leave exactly the signature. A 6-degree tilt. A permanent reminder that our solar system is not as stable as we'd like to believe. About 4.1 to 3.8 billion years ago, the inner solar system was subjected to a catastrophic period of impacts. The moon's surface still bears the scars, enormous impact basins, created when asteroids and comets slammed into it with devastating frequency. This period, called the Late Heavy Bombardment, nearly sterilized Earth. The impacts were so intense that any emerging life would have been repeatedly extinguished. The planet's surface melted and reformed multiple times. What caused it? The standard explanation is the Nice model, named after the French city where it was developed, which suggests that Jupiter and Saturn migrated inward, destabilizing the asteroid belt and sending debris raining into the inner solar system. But recent simulations by David Nesverny reveal a problem. The Nice model alone can't explain the timing or intensity of the bombardment. Something else was needed, an additional gravitational perturbation, something massive enough to scatter not just asteroids, but to fundamentally reorganize the outer solar system. A rogue planet passing through the Kuiper belt would do exactly that. Its gravity would fling thousands of icy bodies inward, creating a cascade of impacts that would last for hundreds of millions of years. The Late Heavy Bombardment might not be ancient history, it might be a warning. In 2016, Konstantin Batygin and Mike Brown announced something extraordinary: evidence for a 9th planet in our solar system. Not Pluto. Something much larger, a super-Earth 5 to 10 times more massive than our planet, orbiting the Sun at distances of 400 to 800 AU. The evidence? A bizarre clustering of orbits among distant trans-Neptunian objects. 6 objects with wildly different orbits, all mysteriously aligned, all pointing in the same direction, as if shepherded by an unseen gravitational force. The probability of this alignment occurring by chance? About 0.007%, essentially impossible. Something massive is out there. But here's where it gets strange. Despite extensive searches using the most powerful telescopes on Earth, Planet 9 has never been directly observed. Some astronomers wonder if it's even there. If it's a real planet that formed with our solar system, we should have found it by now. Unless it didn't form here. Dr. James Vesper from New Mexico State University proposed an alternative. What if Planet 9 is a captured rogue planet, a wanderer that passed too close to the Sun, lost enough velocity to be gravitationally bound, but retained enough energy to remain in an extremely distant, eccentric orbit? This would explain why we can't find it. Captured rogue planets would have orbits completely different from anything that formed here. It would also explain the orbital clustering. A recently captured interloper would still be dynamically evolving, its gravity creating the exact patterns we observe. Planet 9 might not be our 9th planet. It might be our first prisoner. But this represents just one piece of a much larger puzzle hidden in the darkness beyond our solar system. In 2021, the Nancy Grace Roman Space Telescope project conducted preliminary surveys using ground-based telescopes to prepare for its launch. What they found was unsettling. In a small patch of sky near the galactic bulge, they detected 27 potential rogue planets through microlensing events. 27 worlds in a search area representing just 0.00003% of the sky. Extrapolating from this detection rate, astronomers calculated there could be 20 times more rogue planets than stars in our galaxy. Not hundreds of billions, trillions. The space between stars isn't empty. It's crowded with invisible worlds. Dr. Samson Johnson, lead researcher on the project, stated, "We're essentially blind to the true population. For every rogue planet we detect, hundreds or thousands pass by unnoticed." Think about what that means. Right now, at this moment, multiple rogue planets could be passing within a few light years of Earth, moving through the darkness, completely undetected. The galaxy isn't a vast, empty expanse with occasional islands of stars. It's a shooting gallery, and we're standing in it. Scholz's star, a small red dwarf system about 20 light-years away, is unremarkable in almost every way, except for one thing. 70,000 years ago, it passed through our Oort cloud. Research published in 2015 by Eric Mamajek shows that Scholz's star came within 0.8 light-years of the Sun, close enough to gravitationally disturb the trillions of comets orbiting in our solar system's outer reaches. Our ancestors, early humans still perfecting stone tools, lived through this encounter without ever knowing it. But the gravitational ripples from that passage are still affecting us today. Some comets, currently falling toward the inner solar system, were nudged into their orbits by Scholz's star 70 millennia ago. And Scholz's star is visible. We can track it. We know it was here. How many invisible rogue planets have passed through? How many close calls have we survived without ever knowing we were in danger? Astronomers now estimate that a stellar mass object, star or rogue planet, passes within 1 light-year of Earth every 50,000 years on average. That means in the 4.5 billion-year history of Earth, approximately 90,000 close encounters have occurred. Most were uneventful. Some caused minor perturbations, but statistical analyses suggest at least a dozen were catastrophic, close enough to fundamentally disrupt the solar system's architecture. We're here because we got lucky, but luck runs out. In 1984, paleontologists David Raup and Jack Sepkoski published a controversial paper identifying a 26 million-year cycle in mass extinction events. Every 26 million years, like clockwork, Earth experiences a surge in catastrophic impacts and climate disruptions. The dinosaur extinction 66 million years ago, the Permian extinction 252 million years ago. The pattern repeats throughout the fossil record. what could cause such regularity? Some scientists proposed that the Sun has an undiscovered companion star, a dim dwarf nicknamed Nemesis, whose orbit periodically disturbs the Oort cloud, sending comets streaming toward Earth. But extensive searches have found no evidence of Nemesis. The Sun appears to be alone. Dr. Adrian Millot from the University of Kansas proposed an alternative. What if the 26 million year cycle corresponds to our solar system's oscillation through the galactic plane? As we orbit the Milky Way center, our solar system moves up and down relative to the galactic disk, bobbing like a carousel horse. Each time we pass through the densest regions of the galactic plane, we encounter more rogue planets. The math is compelling. At our current galactic orbit, we cross the galactic plane approximately once every 26 to 30 million years. The extinction cycle might not be random. It might be gravitational. A rhythmic encounter with rogue planets lurking in the galactic's densest regions, each passage bringing us face to face with worlds we can't see until it's too late. The James Webb Space Telescope has revolutionized our ability to study rogue planets. In 2023, it discovered something that shouldn't exist: rogue planets with atmospheric chemistry suggesting active geology. These aren't cold, dead worlds. They're generating internal heat, massive enough that their gravitational compression creates temperatures sufficient to maintain liquid water beneath their surfaces. Orphaned ocean worlds wandering the galaxy in eternal darkness. But the most disturbing discovery came from data analysis of stellar occultation events, moments when distant stars dim slightly as unseen objects pass in front of them. Dr. Erika Nesvold's team at the Carnegie Institution analyzed data from the Kepler Space Telescope and found something unsettling: statistical anomalies suggesting massive objects moving through our region of the galaxy. Objects dark enough to be invisible, massive enough to cause detectable gravitational effects, and moving on trajectories that suggest they're not gravitationally bound to any star. One object, designated KBO 2021X, produced a gravitational signature consistent with a super-Earth mass planet passing within 50 AU of our solar system, closer than the Kuiper Belt. When? Between 2017 and 2019. Within the last decade. We didn't detect it directly, we only noticed its gravitational fingerprint after analyzing years of data. By the time we found the evidence, it was already gone. If something that massive can pass that close without us noticing until years later, what else is out there? The evidence extends beyond statistical possibilities into the realm of immediate danger. Let's talk about what actually happens when a rogue planet enters our solar system. The most important thing to understand: it doesn't need to hit anything to cause devastation. Gravity alone is enough. Imagine a Jupiter-mass rogue planet passing through our solar system at 50 kilometers per second, a relatively modest interstellar velocity. It doesn't approach Earth directly. Instead, it swings past Mars's orbit, about 1.5 AU from the Sun. What happens? First, Mars's orbit becomes chaotic. The rogue planet's gravity perturbs Mars, changing its velocity by several kilometers per second. Mars begins spiraling either inward toward Earth or outward toward the asteroid belt. Second, the asteroid belt becomes unstable. Thousands of asteroids are flung into eccentric orbits. Some fall toward the Sun, others are ejected from the solar system entirely. Many enter Earth-crossing orbits. And third, and this is the catastrophic part, Earth's orbit changes. Not dramatically, not immediately, but a velocity change of even 1% is enough to alter Earth's distance from the Sun, changing our climate, disrupting seasons, potentially triggering runaway greenhouse or snowball Earth scenarios. A close encounter with a Jupiter-mass rogue planet passing within 5 AU could change Earth's orbital eccentricity enough to cause million-year climate swings, ice ages, and hothouse periods triggered by nothing more than a slight change in our distance from the Sun. And if the encounter is closer, within 1 AU, Earth could be ejected from the solar system entirely. We'd become rogue planets ourselves. In 2019, researchers at Durham University ran thousands of simulations modeling rogue planet encounters with solar system analogs. Their findings are sobering. Even a distant encounter, a rogue planet passing through the Oort cloud, never coming closer than 1,000 AU, causes measurable long-term effects. Comet orbits destabilize. The planetary system experiences increased bombardment for millions of years. A closer encounter, within 100 AU, passing between the orbits of Saturn and Jupiter, in 73% of simulations, at least one terrestrial planet was ejected from the system. Earth, Venus, or Mars, flung into interstellar space, surfaces freezing within decades as they drift away from the Sun's warmth. Dr. Sean Raymond from the Laboratory of Astrophysics of Bordeaux states it plainly: solar systems are more fragile than we thought. A single encounter with a rogue planet can undo billions of years of stable evolution in a matter of centuries. This forces us to reconsider fundamental assumptions about planetary system longevity, the persistence of habitable conditions, and whether complex life can survive in a galaxy filled with invisible gravitational threats. Some scientists now believe that habitable zones should be redefined not just by distance from a star, but galactic location. Regions with fewer rogue planets. Quieter neighborhoods where planetary systems can evolve undisturbed. Earth might not be in one of those neighborhoods. The Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will revolutionize rogue planet detection. Using gravitational microlensing, it will survey billions of stars, detecting the gravitational fingerprints of rogue planets as they pass between us and distant stars. Astronomers predict it will discover thousands of rogue planets, perhaps tens of thousands, giving us our first comprehensive census of these wanderers. But there's a problem. Microlensing only detects rogue planets after they've crossed our line of sight. It tells us where they've been, not where they're going. To detect an incoming rogue planet before it enters our solar system, we'd need to observe its gravitational effects on objects near it. Background stars shifting position as the rogue planet's gravity bends space. Comets in the Oort cloud beginning to move in unusual patterns. The Vera C. Rubin Observatory, beginning operations in 2025, will survey the entire visible sky every few nights, tracking millions of objects. If a massive rogue planet is approaching, Rubin might give us decades of warning. Might. if we're looking in the right place, if the object is massive enough, if it's not approaching from the galactic south where fewer telescopes can observe. Dr. Matthew Holman from the Harvard-Smithsonian Center for Astrophysics calculated detection probabilities. For a Jupiter-mass rogue planet approaching from typical galactic directions, we'd have approximately 50 years warning before it reached the Oort cloud. But if it's approaching from certain angles, particularly from below the ecliptic plane, we might only detect it when it's already inside the Kuiper belt. That would give us perhaps 5 to 10 years. Not enough time to do anything except watch. Let's say we detect a rogue planet approaching our solar system, a super-Earth, 3 times our planet's mass, on a trajectory that will pass within 20 AU of the Sun in 50 years. Can we do anything about it? The short answer, no. We have no technology capable of altering the trajectory of a planet-mass object moving at interstellar velocities. Nuclear weapons, gravitational tractors, kinetic impactors, these might work on asteroids. They're useless against a world millions of times more massive. The only option would be mitigation, preparing for the gravitational chaos that would follow. Space agencies have begun quietly discussing scenarios, hardening infrastructure, creating strategic reserves, identifying which asteroids might become impact threats once a rogue planet disrupts the inner solar system. But realistically, if a massive rogue planet enters our solar system on a close approach trajectory, human civilization would face an extinction-level event with no technological solution. We could only watch, document, hope that Earth's orbit isn't altered too severely. And if Earth is ejected entirely, if we become a rogue planet ourselves, recent breakthroughs suggest we might survive. Briefly, Earth's internal heat comes primarily from radioactive decay, not from the sun. The core would remain molten for billions of years, but the surface would freeze. Within weeks, the oceans would ice over. Within months, the atmosphere would begin condensing and snowing out. Within a few years, Earth would be encased in nitrogen and oxygen ice hundreds of meters thick. Deep underground, where geothermal vents provide heat, life might persist. Extremophile bacteria, perhaps some animals in deep-sea hydrothermal ecosystems. But humanity? We'd have perhaps a few decades. Time enough to build underground cities powered by nuclear reactors, using artificial light to grow food, recycling everything. A remnant population might survive for generations, but eventually equipment would fail, resources would deplete, the last humans would die in darkness, orbiting no star, on a planet falling through the void forever. Despite the grim scenarios, scientists are working on detection and prediction systems. The Legacy Survey of Space and Time, LSST, conducted by the Vera C. Rubin Observatory, will create a dynamic map of the solar system's outer reaches. Any large object approaching from interstellar space would create detectable perturbations years before arrival. ESA's Gaia spacecraft is mapping stellar positions with unprecedented precision. Anomalies in stellar motion could reveal massive unseen objects, including rogue planets, by their gravitational influence. And future missions, like the Habitable Exoplanet Observatory, HABEX, will have the sensitivity to detect Jupiter-mass rogue planets through direct imaging within 100 light-years. But detection is only the first step. The real work involves understanding galactic dynamics, mapping rogue planet populations, identifying high-risk trajectories. Dr. Gregory Laughlin from Yale proposes creating a gravitational weather forecast, using simulations to predict which regions of the galaxy have higher concentrations of rogue planets, allowing us to anticipate dangerous periods as our solar system moves through these zones. The work is ongoing. The technology is improving, but the fundamental problem remains. We're navigating a galaxy filled with invisible threats, moving at relativistic speeds, and we've only just begun to understand the danger. Here's what keeps astronomers awake at night. Rogue planets aren't just threats, they're opportunities. Some rogue planets, particularly massive ones generating internal heat, could sustain subsurface oceans for billions of years. Life that evolved on these worlds would experience a universe fundamentally different from ours. No sun, no seasons, no concept of day or night, just eternal darkness, eternal cold, and an ocean heated from below by the planet's own gravitational compression. Could such life exist? Almost certainly. Earth's deep-sea hydrothermal vents host thriving ecosystems completely independent of sunlight. Similar ecosystems could persist on rogue planets, perhaps for the entire age of the universe. Now, extrapolate. If there are trillions of rogue planets and even a small percentage harbor subsurface life, the galaxy could be teeming with biospheres we'll never detect. Living worlds wandering in darkness, their inhabitants never knowing stars exist. And here's the profound implication. These wandering biospheres could spread life across the galaxy. When a rogue planet passes through a solar system, it could capture microbes on cosmic dust grains, bacteria trapped in ejected material, or even extremophiles surviving in ice ejected by impacts. These hitchhikers would be carried to the next system, spreading life between stars. Panspermia, the theory that life spreads between worlds, might not require asteroids or comets. It might require rogue planets, invisible vectors of biology, seeding the galaxy. We might be descendants of life that arrived on a rogue planet billions of years ago. If rogue planets are so common, so ancient, so capable of harboring life, why haven't we detected any civilizations on them? The Fermi paradox, where is everybody, becomes even more paradoxical when you include rogue planets. The galaxy should be crawling with life. On planets orbiting stars, yes, but also on the trillions of wanderers between them. Unless something prevents civilizations from arising on rogue planets, or unless we're looking for the wrong signals. A civilization on a rogue planet would have no reason to broadcast into space. They'd have no stars to study, no navigation needs beyond their own world. Their existence would be entirely self-contained. They could be out there right now. Thousands of civilizations, living in darkness on worlds we'll never see, unaware that stars exist, unaware that other life is possible. Two civilizations could pass within light years of each other, one on a rogue planet, one on Earth, and never know the other existed. The most profound implications emerge when we consider what this means for the nature of intelligence, consciousness, and the search for meaning in a universe where most life might exist in permanent isolation. The question isn't if a rogue planet will enter our solar system, The question is when. Statistical models suggest a close encounter, within 100 AU, occurs approximately once every 100 million years. A very close encounter, within 10 AU, occurs once every billion years. These are probabilities, not certainties. The next encounter could happen tomorrow, or not for another billion years. But here's what we know for certain. Somewhere in our galactic neighborhood, right now, there are rogue planets moving through space on trajectories that will bring them into our region of the galaxy. Some are approaching, some will pass harmlessly at great distances, and at least one, somewhere, sometime, will come close enough to matter. We live in a cosmic shooting gallery. Most bullets miss, but eventually the odds catch up. The universe is vast, the mysteries are endless, and in the darkness between stars, ancient worlds fall forever, waiting for gravity to bring them home. Some recent observations suggest we might not have as long as we think. Analysis of orbital anomalies in the Kuiper Belt show perturbations that can't be explained by known objects. Something massive has affected these orbits within the last few thousand years. Whether it's Planet 9, a captured rogue planet, or something else passing through, the evidence suggests our solar system is not as stable, not as isolated as we once believed. The wanderers are out there, silent, invisible, approaching, and we're only just beginning to understand what that means. We began with a simple question: what moves in the darkness between stars? Now we know. Trillions of worlds, orphaned planets ejected from their birth systems, condemned to wander the galaxy forever. Some are larger than Jupiter. Some harbor subsurface oceans. Some might even carry life through the cosmic void. They outnumber stars by thousands to one. They're invisible, undetectable, approaching from all directions. And our solar system, our fragile collection of worlds orbiting an ordinary star, sits in their path. The evidence is clear. Rogue planets have passed through before. They left fingerprints: the scattered disk, the tilted solar system, the clustered orbits of distant objects. They might be here now. Planet 9, if it exists, could be a captured wanderer rather than a native world. And they will come again. The mathematics is unforgiving. The galaxy is too crowded, space too small, time too long. Eventually, inevitably, another encounter will occur. We can't stop it. We can barely detect it. All we can do is watch, learn, and prepare for a universe far more dynamic and dangerous than we ever imagined. But perhaps there's hope in understanding. The same rogue planets that threaten our stability might also carry life between stars, seeding worlds with biology, spreading the possibility of consciousness across the galaxy. We are not immune to cosmic chaos, but we are witnesses to it, participants in a universe where nothing is permanent, nothing is safe, and everything is in motion. The wanderers fall through darkness, the stars drift through space, and somewhere between chaos and order, life persists, on worlds bound to suns and worlds condemned to eternal night. The universe is vast, the mysteries are endless, the journey continues, and in the darkness, something moves.